Welcome to Great Moments of Serendipity. Okay, just another reminder before we get completely started here. Down in the description of this video, if you expand it by hitting the show more, you will have a link to this file. It's a 3-page file that we're going to take our notes on. You'll also have a link to this file, which is the homework problems. There's only 10 in this set, not a big deal. And yeah, that's what's down there. So what do you say we get started right now? What was I talking about? I was talking about serendipity and great moments of them and so on. So come back in time to the year, I don't know, 1600 something. I don't know if it was like 1610, 1620, 1630. I don't know, I'm guessing. And you're a philosopher, mathematician kind of guy, a French mathematician, philosopher kind of guy. And you're lying awake in bed and you're looking up. It's the morning, you're looking up, and this is your ceiling. So this is the view that you see of your ceiling. And on your ceiling, you happen to notice on this fine morning a bug. There's a bug. The bug is right there. And as you continue to look up at the bug, you notice the bug starts to move. And he follows a certain path. It doesn't have to be straight. Maybe it goes like this. I don't know what it does. But the bug follows a certain path. Now, you're a 1600s French mathematician, philosopher kind of guy. What kinds of thoughts come to mind when you look at this thing? Well, I'll tell you what Descartes thought. Descartes is the guy I'm talking about here, René Descartes. He asked himself, you know, how could I use mathematics to describe this bug's path? Or this bug's position even. How could I use mathematics? Now, we had geometry at that point, and they even had algebra at that point, but at that point, the two subjects were completely separate. Descartes' genius breakthrough idea was to combine algebra and geometry into a single subject, which is called analytic geometry. And I'm serious, I was reading a magazine of history's greatest breakthroughs, and they nominated this one as the most important breakthrough in human history. Is this invention of what you're going to say, oh, you mean the XY axis? Yeah, you know, the XY axis. This was a brilliant idea. To be the first one to come up with this was like really something. So his solution to specifying the bug's position was to say, well, I'm going to need two pieces of information. I'm going to need a piece of information which tells me how far is he from this corner of the ceiling? Maybe call this the origin, just to give it a nice name. And you can say, well, you know, look, x is 1, 2, 3, 4. The bug is at x equals 4. But the bug is also at y equals, that's a 0, 1, 2, 3, 4, something like that. And so you can say, hey, at this specific moment, the bug is at coordinates 4, 4. And then if the bug moves, you can say, well, you know, later on the bug was over here at, I don't know what this is. Let's call this 10, 7. So you can say, yeah, man, 2 minutes later the bug was over here at 10, 7. But then he took it even further and he started coming up with the idea of making equations that represented that path. In other words, formulas, equations that basically relate the x coordinates and the y coordinates. So, you know, you can plug in a value of x and figure out what's the value of y at that point. And if you plug in a different value of x, you get a different value of y and so on. So that was his great breakthrough moment of serendipity. So kind of take it for granted that we're going to be looking at all kinds of formulas and equations that represent graphs, okay? Now, before we get there, let's just kind of back up a step and ask ourselves, what if I had like a little equation like this? What would that look like if I graphed it? Little old equation. So in other words, we're just going to start with equations and say, I wonder what that bug path would look like. Look at a different equation. I wonder what that bug path would look like. And we're going to actually make a very interesting kind of a, what's the word, conclusion. We're going to draw an interesting inference. It's going to be cool. So here's a nice simple equation that's about as simple as you can get, really. y equals x. So what we typically think of doing is thinking in terms of a table of xy pairs, and you plug in things like, you can plug in anything you want, really. I think I'm going to plug in these values. I'm going to plug in x equals -4, -2, 0, 2, and 4. That'll be my standard for a while. And then you say, well, according to this formula, when I plug in x equals -4, I will get y is the same thing, -4, right? And if I were to plug into this formula x equal to -2 and plug it in right there, it would tell me that y is equal to -2, and I would put it right there. So it's basically telling me that x and y are always the same, right? So if you plug in x equals 0, you get y equals 0. If you plug in x equals 2, you make that a 2. Well, this will have to be a 2, right? So when x is 2, y is 2. So this really is one of the simplest equations you're ever going to come across. The old x and y are the same thing equation. Now what you do is you plot those points and see what kind of bug path we got here. So when x is a -4, y is a -4. So this is our x-axis, this is our y-axis. This is the Cartesian, named after Descartes, the Cartesian convention. X goes to the right, y goes to the north, and this we call the origin. It's the point where x and y are both 0, 0, 0. And then we say, okay, what's this point? Maybe I'll call it point A. Point A is when x is -4, so you have to go back this way. 1, 2, 3, 4. Then I get y is -4. 1, 2, 3, 4, down to here. And this is where point A ends up. Then you do the same thing here. I'll call this point B. When x is -2, so you start at the origin, you go back -1, -2. And then y is also going to be -2. So starting here, you go -1, -2. And so here's your point B. So I'm assuming this is familiar, that you're not seeing this for the first time. I would really doubt that you are. Even if you're just working in Alex, I'm sure you've seen this already a bit. So here's the point 0, 0. I could call that point C, I suppose. Here's the point 2, 2, point D. It says that when x is a +2, so this is the positive x direction, this is the positive y direction. When x is +2, 1, 2, I'm over here, but then I also go y is +2, 1, 2, and here's my point D right there. And finally, point E would be at the coordinates 4, 4, which is over here, 4, 4. And then what we do is we join these points together and we say, oh, nice bug path we got there. So this is like if the bug was going diagonally across your ceiling, I suppose. It would look like that. By the way, it's nice to draw the arrows at the ends. The arrows show that it keeps going. Like this equation doesn't stop just because just because the last thing I plugged in happened to be x equals 4 doesn't mean I couldn't have plugged in x equals 28. And I would get y equals 28, right? So way out there someplace, I've got this other point, 28, 28. So we draw arrows to show that it keeps going like that. And by the way, this habit, what do you want to call it? This practice of joining the points into a straight line, that's got a lot of meaning to it. Why do we join the points with a straight line? And it's out of recognition that these are not the only 5 points on the line, right? That you could plug in x equals 1 and you will get y equals 1. You could plug in x equals 1.5 and get y equals 1.5. You could plug in x equals 1 3/4 and get y equals 1 3/4, and so on. So really, there are a million, jillion, schmillion points here, because you can plug in x equals 1.5, 1.5001, 1.5002, and so on. You could plug in millions and jillions of points, and all of those points will blur together to look like a line. It's really a million, jillion points all blurred together. But that's why we joined them. It's because there's so many of them, it looks like a line. Okay, so that was a fun one, right? Y equals x. Think of that as our baseline case. Y equals x is a 45-degree line through the origin. There it is. Y equals x is a 45-degree line through the origin. What happens if we do this. That's a little bit different, right? That's y equals 2x. Well, let's just think in terms of our xy table again. And I'm going to plug in the very same values that I did before. Let's see, can I zoom out a little bit? I'm going to plug in the very same values for x that I did before. -4, -2, 0, 2, 4. -4. These are just made up, by the way. You could make up other ones. You could go -4, -3, -2, -1, 0, 1, 2, 3, 4. You could go by halves. You could go by 40s. You could go by whatever you want. As long as you plug something in so you know what's going on. So anyway, when I make x equal to a -4, that means I'm plugging a -4 in here. Notice I'm going to have 2 times a -4, which is going to give me a -8. Wow, -8. Now when I plug in x equal -2 right there, I multiply the 2 times a -2 and I get a -4. Okay, that was cool. Now let's plug in a 0. Now if you plug in a 0 here, notice this is telling us to multiply 2 times 0. 2 times 0 you get, well, 0. And you just kind of keep going until you're done with the whole table. So plug in x equals 2 right there. The equation is telling us to multiply 2 times 2. 2 times 2 is 4. Awesome city. We're making some progress. And lastly, I'll plug in x equals 4 right there. Plug in a 4 right there. 2 times 4 is 8. And that's enough points to get the idea. We can start plotting these points. So I'm going to come on over to here now. And I'm going to say when x is -4. So again, this is the origin. This is the point 0, 0. This is the positive x direction going to the right. This is the positive y direction going up. So this point here, -4, 8, means that x is -4. You just go 1, 2, 3, 4 in the negative direction. And then y is -8. You go 1, 2, 3, 4, 5, and we're off the charts. So I'm not even going to try to draw it because it's way off the charts. So never mind, let's draw this point. Point B, x is -2. So remember the origin right in the middle where the crosshairs are, that's 0, 0. So x, go in the negative x direction by a distance of 2. You get to here. Now go, it says -4 for y. Huh? So you go in the negative y direction, a distance of 4. You end up here, and that's our point B. Cool, cool, cool. By the way, 0, 0, which is the origin, that's our point C. So we already got that right there. And then let's see, this will be another point we can draw, 2, 4, call it point D. So x is +2, means you come out to here on the x-axis, and then y is, not what I wanted to do. And then y is 4, means you come up y in the, you count up 4 steps in the positive y direction. You end up here. So there's your point D. Get this stuff out of the way, out of the way, out of the way, out of the way, out of the way. Okay, cool. And you'll notice that once more we are falling on a nice straight line. And if you have any doubt, you can always prove it to yourself by saying, well, what would happen if I plugged in x equals 1? If I plug in x equals 1 here, I get 2 times 1 is 2. When x is 1, I come up to 2. Yeah, it works. I'd be on that line. So you can feel pretty confident to just join those points. And like I was saying earlier, put arrows on the ends, please, to show that the line continues in both directions. Okay, question now. We've done 2 lines. We did y equals x, and now we just did y equals 2x. What's the difference between these 2 lines? Well, they both go through the origin, but this one is steeper, right? Steeper line. That's a P. Steeper line through the origin. It still goes through the origin. It goes through the point 0, 0, but it's steeper. Huh. Okay, that's cool. Let's try another one. Y equals -12x. Ooh, -12x. Well, again, especially when you're first playing with straight line type stuff, it's best just to use an XY table. XY tables won't lie to you as long as you do this part right, you do the old, I'm going to make x equal to a negative 4. So that means I'm going to have a negative 1/2 multiplying a negative 4. Now negative times negative is positive. Half times 4 is the same as what's half of 4. Half of 4 is 2. So that's a 2. And then you plug in again. You say, now I'm going to plug in x equals negative 2 right there. So that's going to be a negative 1/2 multiplying a negative 2. Negative times negative is positive, and half of 2 is 1. Cool, cool, cool. Cool, 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 cool. Now let's plug in. My favorite thing to plug into any equation is a 0. If you plug a 0 here, you got a half times a 0. Anything times a 0, it's a 0. Okay, that was, see, I told you that would be fun. And now let's plug in, where are we? We're right here. We're going to plug in x equals a positive 2. Now, you always want to be careful when there's negatives in your equations. So we've got a negative 1/2 times a positive 2. Well, a negative times a positive is a negative, so we're getting a negative answer for sure. And half of 2 is 1, so actually we get negative 1. Think. And lastly, let's plug in x equals 4. It goes right there. And so you've got a negative 1/2 multiplying a 4. Again, a negative times a positive is a negative, and half of 4 is 2. So now we got some nice points. Let's see what we're looking at here. Start graphing these things. When x is negative 4, y is 2. I'm going to call that point A. So again, here's my origin. There's the positive x direction. Here's the positive y direction. This is the point 0, 0. Okay. X is negative 4. 1, 2, 3. I'm here. Y is positive 2. 1, 2. I'm here. I end up here. Get rid of those dots. Now what do we got? X is negative 2. Y is 1. So starting at the origin, I go negative direction, 1, 2, and then I go up 1. Here's my point B. And here's my point C, actually at the origin, so that's cool. And then here's my point, I'll call it point D. When x is positive 2, so from the origin, you would count out positive 2 in the x direction, and then you would go negative 1 in the y direction. You would end up here. So this is point D. Let's see if the eraser is going to work. Oh, it did. Cool. And finally, point E is at 4, negative 2, which means go in the x direction to 4, in the y direction to negative 2. You're going to end up right there. It's another one of these nice, wonderful straight lines. It's a straight line. Put arrows on both sides. Okay, and now the question. Compare all 3 of these lines together. The line y equals x was a 45-degree line through the origin. The line y equals 2x was a steeper line through the origin. And now the line equals negative half x. For one thing, it's kind of going down instead of up. That's what the negative did for you. It made the line go down instead of up. When I'm talking about, like, if you read like a book, you read from left to right. It's going down and you read from left to right. And the 1/2 being kind of a small number made it kind of not steeper, but less steep than the 45-degree line. Get rid of some of this green stuff here. And so what would we conclude? I guess we'd say something to the effect of y equals negative 1/2 x, less steep, still through the origin, but goes down. That's the big thing. It goes down. Negative slopes will always go down. That's worth its own notation. Negative slopes go down. So again, we're talking about as you read left to right. As you read this line left to right, it's going down. If you have a negative slope, that's what's going to happen. So we got a couple things here. So if you have a nice, if your x has a what's called a coefficient, a 2, not just 1x but 2x, that made it steeper. You know what's happening is when x goes up by 1, y goes up by 2 because of the 2. When x goes up by 1, y goes up by 2 again because of the 2. You know what's happening here? When x goes up by 1, y goes down by a half. When x goes up by 1, y goes down to a half. So this number here, this slope, is telling you, that's what it's called, is the slope. It's telling you how much x changes, or how much y changes when you step 1 in the x direction. We'll define that formally at the top of the next page. First, let's look at this last equation here. Notice we got this y equals negative half x. That's the same as this. It's just that we get this extra thing here with the plus 3. So let's see what happens there. So you go x, y, let's just plug in the same values. Negative 4, negative 2, 0, 2, and 4. Now before, when we plugged in negative 4, we got y equals 2. But now we're going to get y equals 2, and then we're going to add 3 to get 5. I'll do the next one. 5. Okay, 5. I'll do the next one this in brute force way. I'll plug in a negative 2 right there. So negative 1/2 times a negative 2, and then you add 3. Well, the negative times a negative is a positive. Half of 2 is 1. And then you add the 3, and you get 4. When you plug in 0 for x, you get 1. You get 1/2 times 0, but then you add 3. That's the same as 0 plus 3. You get 3. When you plug in x equals 2, negative 1/2 of 2 plus 3. Negative 1/2 of 2 is negative 1, plus 3 is 2. And you can almost tell what's going to happen just by looking at this table here. If you look at this table here, 5, 4, 3, 2, yeah, that pattern really is, that's a real pattern. It's going to be a 1. And if you doubt me, just plug in negative 1/2 times 4, add 3, you will get 1. Okay, so what's this line look like? I'm going to call this the point A. When x is negative 4, y is 5. It's a little bit off the chart here. I had to go 4 in the negative x direction, 5 up. The point B is at x equals negative 2, 1, 2, y equals 4, 1, 2, 3. Here's the point B, that's the point A. Okay, point C is at 0, 3. X is 0, y is up here at 3. There's point C. Point D is at the point 2, 2. Point E is at 4, 1. So we got a line, all right. Notice it's the same steepness or the same slope as what we had over here. This line and this line have the same steepness to it, and that's because they both have this negative half in front. That's what makes the line have a certain steepness, is whatever number is multiplying x defines the, well, what they call it the slope of the line. What did this 3 do? What this 3 did, this 3 right here, is it made the line go up by 3. So instead of starting here at the origin, 0, 0, it started up here at 0, 3. And notice every single point on the line is shifted up by 3, basically. So the 3, adding 3, shifts it up 3. And in common parlance, we will say the y-intercept is 3. Because when you start at x equals 0, instead of getting y equals 0, we got y equals 3. The whole line got shifted up. This is called the y-intercept. Okay, cool. So the best way to learn graphing is to get your hands dirty making a bunch of graphs, and so we've started to get our hands dirty making some graphs. Now what I want to do is I want to summarize our observations here. We were just making all these really nice observations, right? What's the effect of putting a 2 multiplier? What's the effect of making a negative multiplier? Of making a plus 3 added on and all this stuff? Well, we could formalize it by saying that y equals some number times x plus some other number. That's what we've been looking at. That is going to be called, well, it says it right there, slope-intercept form of a line. I suppose I should put that in there, where the m number is called the slope. Sometimes it's called the rise over run. I like to say it's how much y changes when x goes up by 1. That's a parenthesis. So here, when x changes by 1, what happens? Y came down by half. When x changes by 1, y comes down by half again. When x changes by 1, y comes down a half again. That explains why we have what the negative half multiplier is doing. Okay. You could also say rise over run. So rise over run, you could say, well, instead of thinking of these little steps, think in terms of I rise -1, which means go down 1 over 2, go down 1 over 2, go down 1 over 2, and so on. So you can look at it either way. It's a ratio, that's what's important. But it tells you how steep the line is the main point there. And then the b number is the y-intercept. Again, it was it shifted the line up and down, and by doing that, instead of going through the origin, it's going to go through somewhere else on the y-axis. It ends up, we call that the y-intercept. I'm going to, in parentheses, say where you start when x is 0. Okay. Slope-intercept form of the line. Now, all of these equations that we looked at over here, like you could say this one, the slope was -1/2. I went down 1 over 2, down 1 over 2. +3, because the y-intercept is right there at 3, and so on. This line here, the slope was 2, so up 2 over 1, up 2 over 1. And there was no number added here, so it's like the y-intercept was still 0, and so on. Okay, so it works like a charm. So to get used to this a little bit better, let's practice using it the other way. So take a look at this line right here. We can actually write the equation of that line just by looking at this graph. We can say y equals, and we got to figure out, well, what's the slope number and what's the y-intercept number? To get the slope number, what you want to do is you want to try to look along the line until you find a point where, here's a good point. See how it crosses right on the what do you call these, grid lines? It crosses right on the grid line, and then here's another point where it crosses right on the grid line. So let's use those 2 points to figure out the slope. Now slope is basically rise over run. Notice to get from this point to that point, and you want to do this to the right, just like you're reading a book. How does it change as I go to the right? To go from this point to this point, I could go up by 2 and then over by 4. And that ratio of rise over run is what we call the slope. So m is rise over run is +2 over 4, which you really should reduce to 1/2. So the slope is 1/2. The m number, the number multiplying x, is 1/2. Now, get the y-intercept. Well, you look, here's the y-axis, here's where it crosses the y-axis, and it crosses the y-axis at -1, and that's your b. And that's all there is to the b. Oops. That's all there is to the b. Okay, so that was your m is 1/2, that was your b is -1. That's the equation of that line. So you can tell just by looking at it. Let's look at this one. Again, you try to find 2 points on the graph that cross the grid line. That's a pretty good cross right there. and maybe this is another point where it crosses the grid line pretty nice. So I'm going to look at going from this point to this point. First go either up or down and then go to the right. So I'm going 1, 2, 3, 4. I'm going 5 down and I'm going 3 to the right actually. So the slope here, rise over run, is a -5 over a +3. It's -5/3. If I want to write my formula, I'm going to start with -5/3 x. Don't forget to get the y-intercept in there. If it goes through the origin, you'd be done, but it doesn't. Well, it looks like we have b equals -1 again here. So to finish this equation, I would really want to say -1, like this. Okay. Tell you what, why don't you pause the tape right now and try these two lines yourself, see if you get the same answers as me. Pause. Unpause. Well, for this line, I'm thinking I should go from this point over to this point. So I'm going up by 1, over by 3. So my slope, rise over run, is up 1 over 3. I have a slope of 1/3. So y equals 1/3 times x, and then I got to get the y-intercept. And the y-intercept, it turns out, is also 3, right? Here's 0, 1, 2, 3. So the y-intercept is 3, so I just add 3 onto that to say, don't cross at the origin, cross at 3. This one, find 2 points. There's a point, that looks good. And maybe that's a point, that looks pretty good. And then you go up or down, and then to the right. So I've got to go down 4, it looks like, -4, and over to the right. And so my slope, which is rise over run, is going to be a -4 over 1, which is the same as a -4. So my m number, which multiplies the x, is -4. So I have y equals -4x. But then get your y-intercept too, because it's not crossing at the origin, it's crossing here. And you look on the y-axis and you say, well, I'm going down to -1, -2. My b is -2. Just add a -2 on the end there. And there's that line. So hopefully you're starting to dig these equations of lines. Slope-intercept. It's huge. Slope-intercept. Huge, huge, huge. So we're going to end with just a couple of little applications here. Now now that you're kind of playing around with slope and intercept, slope, how much does it change when x goes up by 1, how much does y change? And intercept, where do you start when x equals 0, right? Just keep those two facts in mind, and now let's read this along. Biff spends $40 to buy all the necessary stuff to get started. That's what he starts. He starts by spending. $40. Can you say y-intercept? That's where he started. Before he manufactures any widgets at all, he had to spend $40 right up front. So that is definitely suggesting, hey, I could be a y-intercept. Meanwhile, each widget, which means every time I make a widget, it's going to cost 50 cents to produce. Each widget costs 50 cents. So you spend 50 cents more for each widget you produce. And this idea of how much does y change when x changes by 1, right? How much more do you spend when you make another widget? Can you say slope? Hopefully you're starting to get sort of an intuitive connection like, hey, you know what? That might be right. But if you're a little uncertain, maybe the graph can convince you. Let's say we have x widgets going this way, and this is going to be y bucks that we spend to make those widgets going this way. And this is start at the origin, 0, 0, meaning that, well, the origin would mean that 0 widgets cost $0, except that's not where our line starts, because when we make 0 widgets, we actually have to spend 40 up front. Up front, we spent $40. That's where we cross the y-axis, right there. We start at $40. Then, when you make a widget, you're going to have to go up 50 cents to make one widget. Up 50 cents to make one widget. Up 50 cents to make another widget. Up 50 cents to make another widget. See how this defines the slope? I'm going to say right here the slope is 50 cents, which is $0.50, to make another widget. And so we can actually write the equation of that line. mx plus b, the m number is 0.50, and the y-intercept is 40. And so that becomes our little cost equation. That's how much it costs to make a bunch of widgets on this machine. Now, after a while, after you've played with enough straight lines, you'll be able to look at an equation like this and go, oh yeah, that makes total sense. It's 50 cents. Start at 40 and rise by 50 cents. But at first, of course, you're not going to know quite whether to trust it. So at first, what you want to do is run some arithmetic to check against the formula. How much would it be to make, and then you can just kind of make up a number, 100 widgets. Do it by arithmetic. Arithmetic, you say, well, 50 cents each is, well, 50 cents times 100 widgets would be 50 bucks. And then add the 40 for the startup, and it's 90. So doing the arithmetic, you say, well, it's 90 bucks to make 100 widgets. And then check against the equation. Say, well, if I were to plug a 100 right here, notice what the formula is going to do. The formula is going to take 50 cents times 100, which is exactly what we did to get the 50 bucks, and then it's going to add 40, which is exactly what we did, right? So actually the equation is doing exactly the same thing that we would do if we were just doing it arithmetically. But this is a little more slick because you've got the equation and you can program it in Excel and you can do all kinds of funky things. Let's do another one. If you dare, you could pause the tape and try it here. I'll pretend you paused and you have unpaused, eager to check your answer against mine. Okay, what do I got here? Biff profits $1.25 on the sale of each hot dog. So each hot dog gets you $1.25. Okay, you make $1.25 for each hot dog. This idea of for each has got to be making you think of slope. One hot dog is $1.25. Meanwhile, it says, oh, wait a minute, it cost him $3.50 to get all set up and legal. That's the starting point, right? Starting at $350. Actually, wait a minute, notice these are kind of going in opposite directions here. This is I'm getting $1.25. This is I'm spending $3.50. So since they're going in opposite directions, let's call that negative. Starting at negative $3.50, and if you're starting at that, that's got to be having you think of y-intercept. And if you want to be really sure that that's what's going on, you can just start to make a nice little graph. I always make a graph, by the way. I trust a graph more than words any day. So anyway, we're starting, whoa, we're starting $350 in the hole, so I'm going to have to kind of expand this a little bit, way down here. So we're starting down here by spending $350. So this is my profit. And I suppose if you spend money, that is a negative profit, right? Because you're not making any money if you spend it. So you spent 350 bucks. So your profit is actually starting out negative. But every time you sell a hot dog, you can add $1.25. Another hot dog, another $1.25. Another hot dog, another $1.25. Another hot dog, another $1.25. So basically, you go up $1.25 for every one hot dog that you sell. That is the slope. 1.25 over 1 is the rise over the run. So the slope is $1.25. The y-intercept is here at negative 350. So that's our b, that's our m. We can actually come over here and write our nice little equation very nicely. mx, and then you put the b in, which is actually a negative 350. Cool. So these things start to like really pop together. Once you get the idea of, start at this and then change by this much each hot dog, each step of the way, each whatever. In business lingo, they would call this the fixed cost. Maybe I'll write that down. The fixed cost, because you have to spend it, and then once it's spent, you're done spending it. Actually, that's not called fixed. Let me go back to this. Made more sense actually at the previous example, I think, because here we're talking about profit, fixed profit. I don't want to say fixed profit. Here we were talking about costs, so this would have made a lot of sense to say the $40 was the fixed cost, because you had to spend the 40 and then you were done spending it. And then this was the variable cost, because every time you make a widget, you have to spend another 50 cents. So it's variable in the sense that it depends how many widgets you make. It's the same for each widget, but it depends how many widgets you make, the variable cost. Down here, I guess I could say fixed profit. It just sounds weird. And this would be the variable profit. But I'm going to put this in question marks because although it makes sense to me to say that, it also sounds awfully funny. So anyway, I think there was another part to this question. It said, how many hot dogs must he sell to break even? How many hot dogs must he sell to break even? Okay, so come on, you. Breaking even. I'm going to put our formula to the test by first just do the arithmetic. To break even means what? It means you recover the $3.50 that you spent. So you get $1.25 per hot dog. So I'm going to say at $1.25 each. How many would you have to sell to get $350? So you go 350 divided by the $1.25 tells you that you should sell. Oh, I did this. What did I get? I did do this, right? Oh, for heaven's sakes, are you serious? Oh, there it is, 280. You're going to have to sell 280 hot dogs to break even. 280 times $1.25 each is $350. But notice that the formula by the equation, break even means zero profit. Remember, you start with a negative profit because you had to spend $3.50. When the profit gets to zero, you're breaking even. So in other words, set y equal to 0. And if you set y equal to 0, in this equation here, you'll have 0 equals $1.25 x minus $3.50. 0, come on, you. 0 equals $1.25 x minus $3.50. And you solve this for x. So you add $3.50 to both sides. And then to solve for x, you'd want to divide the coefficient on both sides. And here's the cool thing. Notice this amounts to doing exactly what we did here. 350 divided by $1.25. 350 divided by $1.25. You're going to get the same answer, of course. You're going to get that you have to sell 280 of these things to break even. And personally, I've always loved this part. The part that you can do arithmetic. You can do the arithmetic and figure it out, but somehow the algebra knows. The algebra knows the same thing. So you can use arithmetic, which means trying to figure it out in your head, or if you have an equation that you trust, you can use the equation because the algebra will know what the answer is. Okay, well, I hope you're enjoying this nice little introduction to straight line stuff. Okay.